Hi everyone, welcome to another video lecture. Before we get started, I just wanted to give you an opportunity to say hi to Mitch, the Russian tortoise. If you haven't been a part of our regular class time sessions, you might not have seen Mitch and he wanted to say hi, so say hi Mitch. All right, I will put him back and we can really get started because today's lecture is on the declining population paradigm. We've been talking a lot about stochastic processes that can cause issues for populations, especially small populations. We've talked about demographic stochasticity having a disproportionate effect on really small populations. In addition, environmental stochasticity also has a disproportionate effect on small populations in one way, and that is if you have a small geographic range, you're much more vulnerable to environmental stochasticity, especially major catastrophic events like hurricanes, droughts, because if you're in a small geographic area, it's more likely that that entire geographic area, say a small island, will be all affected by a single catastrophic event. Whereas if you have a spread out population over a large range, it's likely that only a small portion of that range will be affected by that environmental stochastic process, like a catastrophe. All right, so we started off this discussion, or this lecture, with a discussion on the intrinsic rate of growth for species. Now, most species, all species, I would say, have the capacity, the capability of growing exponentially. Because if they don't, that is, Rmax should be positive for most species. Because if their Rmax is negative, the population's declining and it won't last very long. So if it's on the Earth at this time, it means at some point it was able to sustain growth or remain a stable population, which means that the R max should be positive. It should be above zero. So today we're going to talk about those processes that cause species that have maybe large populations and the capability of growing with R max being above zero. What processes cause those populations to experience declines? And this topic is called the declining population paradigm. All right, so here's the declining population paradigm. And again, most species have capability of growth. So given that most species are capable of sustained growth and attaining large population size when conditions are favorable, how do populations get small in the first place? That's the topic of this discussion. That's what the declining population paradigm is all about. Why are many populations declining despite their intrinsic ability to grow? Is it random? Are these random processes, or are these more systematic, deterministic processes? So the answer, of course, is that under ideal conditions, all populations are capable of growth. We're just talking about inflows and outflows, births and deaths. And if mortalities end up exceeding births under the current conditions, the population will decline and potentially go extinct unless those unfavorable conditions are reversed. So we've talked about stochastic threats to small populations, loss of genetic diversity, demographic stochasticity, catastrophic events. These affect small populations. Large populations are pretty resilient to those kind of threats. But large populations, just like small populations, can be threatened too. And those factors that threaten large populations are often deterministic in nature. They're not stochastic. They're not random. What do we mean by deterministic threats? Well, we're going to talk about some examples below. You can see the overharvest example is coming. You can see at the bottom of this page. That's one example of a deterministic threat where we're, in this case, through human economic activities, we are killing directly individuals in populations, and that can tip the balance in favor of deaths versus births, and the population will decline and potentially go extinct. So that's one example. So the declining population paradigm, when we refer to that, what we're talking about is this focus on factors that make large populations small. That is, both populations that are large, lots of individuals, or populations that are extremely spread out and have large geographic ranges. What factors can cause those populations to decline and ultimately become small? So the declining population paradigm is the study of those deterministic processes that cause population decline, that tip the balance between births and deaths, and how those processes may be reversed through effective conservation management. So let's just talk about some of the factors that can tip the balance, so to speak, so that that can turn a growing or stable population into a declining population, even a very large one. And overharvest is a obvious example. Here's a good an example you've probably heard of with the Atlantic cod stocks. This is particularly the West Atlantic region, so we're talking like Newfoundland, and you've probably heard that those cod stocks, which formed a really important part of the economy of the northeastern United States and eastern Canada, and has since, in 1992, was basically completely banned. Like, you couldn't harvest anymore. So what happened there? Well, it's pretty simple story, basically. Throughout the late 1800s, early 1900s, the harvest seemed to be sustainable because they didn't really use motorized ships that much. They didn't have really high-tech equipment. And then by the 50s and 60s, the motorized trawlers started going out and not only catching a huge number of fish, but also destroying the benthic habitat. And basically, there was a double whammy there. And ultimately, by the 80s and 90s, the stock was basically not. It was degraded, and we couldn't really sustain an economic harvest. So that's an example. I encourage you to read more about it. It's an interesting story of how this very economically important fish stock has basically disappeared, and people are concerned that it may not even come back because the balance ecologically may have been tipped now in favor of some other animals. In fact, some of the smaller predators now are so overabundant that they'll consume the eggs of the cod, and they're not allowing the cod to rebound even with low harvest rates. All right, so that's one example. Overharvest, a deterministic process that can cause very large populations like the Atlantic cod to collapse, essentially. Habitat loss and degradation. This one's pretty obvious. If you destroy habitat, you can easily tip the balance between births and deaths. There's just not enough habitat to sustain life in many cases, and populations will crash. So that's pretty obvious, but that really is the primary process that is causing so many populations on Earth today to decline. So it's important to bring it up. Pathogens and parasites. This one kind of hits kind of close to home right now. And all animals, including humans, can be affected by pathogens and parasites, and are, constantly at war with pathogens and parasites. Most of the time, their populations are still able to grow, but sometimes really virulent pathogens come in. Oftentimes, invasive pathogens or parasites from other parts of the world get introduced into a population that's naive to those pathogens and parasites, and can wreak havoc on populations. So one example that's current is the white nose syndrome that is affecting many bat populations across North America. We first noticed it in New York State, and it's been spreading out over the last decades and totally devastating a lot of cave roosting bat populations, like the little brown bat. So it's a pretty sad story, and it is an ongoing story. And, little brown bats were one of the most common bat species in North America, and now there's talk of including them on the endangered species list. That disease, that white nose syndrome, has definitely tipped the balance, and deaths often exceed births now for that species. All right, climate change. Another kind of example of a deterministic process, essentially, that can tip the balance in some cases between a growing population and a declining population. Climate change is happening at a rapid rate, a rate that's pretty unprecedented in geologic history, and we can see this is over the past, say, 140 years or so. The average climate over the past 140 years or so was much cooler than it is now today. So this map shows a climate anomaly between current climate conditions and the average climate conditions over the past 140, 150 years. And almost around the world, climate has warmed by significant degree, like over 1 degree Celsius, often 2 degrees Celsius. And it's just getting more and more severe. So this is definitely a factor that for many reasons, can tip the balance. And potentially it's an indirect effect, because maybe climate change will allow a new parasite to invade an area that it hadn't been able to invade before. So really, parasites the main cause of the population decline, but climate change is the ultimate factor that caused it. Exotic invasive species, another factor that can tip the balance. And you've heard about many examples of exotic invasive species potentially tipping the balance. They can be plants, they can be animals. Cheatgrass is a good example from the Great Basin. The bullfrog is an interesting example, because I'm from the East Coast, where bullfrogs are native. So I would go out to ponds and hear bullfrogs and enjoy listening to these native animals in their native ecosystems. But in California, for instance, bullfrogs are wreaking havoc on fish and native amphibian populations. They've been introduced, and they shouldn't be there, and they're there now, and they're out competing native amphibians, and they're eating the eggs of native fish. They are, just causing issues ecologically and potentially tipping the balance for native species. Pollution, another factor that can tip the balance. In many cases, these kind of chemical pollutants will cause populations to end up declining when before the habitat was perfectly fine. This is an example of habitat degradation, for instance. All right, so those are maybe not a complete list, but a fairly complete list of the major factors that are causing decline of population. So let's talk about the declining population paradigm a little more at this point. So we have the small population paradigm. We've talked about the small population paradigm. It focuses on those stochastic factors that can cause small populations to become extinct. Now we're talking about the declining population paradigm that studies those factors that can cause large populations to become small. Which one's more important? So, do you think the declining population or the small population paradigm is more important to study? Now, the terms were actually introduced in this paper, which I've already posted on our Top Hat lecture page. But I do very much encourage you to read the paper. It's an easy read, and it's a foundational paper for conservation biology, and it raises some really interesting points that are still very relevant today. It's by Graham Coley. It was published in Journal of Animal Ecology in 1994, and he really coined the terms small population paradigm and declining population paradigm. And In the paper, he not only coined the terms, but he kind of presented a bias in favor of one of these two paradigms. And let's see if we can suss out what his bias was. So this is a quote directly from the paper. Conservation biology has two threads: the small population paradigm, which deals with the effect of smallness on the persistence of a population, and the declining population paradigm, which deals with the cause of smallness and its cure. So can you detect a bias in that quote? And what do you think? I'd like you to post a comment on the Top Hat site and just let me know what you think. Which of these two paradigms is more important for conservation biology, or are they both equally important? Coley clearly is saying that the declining population paradigm is more important because that is the science of curing the malaise that is causing populations to become small. And he's kind of downplaying the small population paradigm. So, what do you think? In the next lecture, we will go through an example in Insight Maker of how these deterministic threats affect population and how we can model those threats. I will see you in that next lecture.